I'm going to talk a little bit more about oxidation reduction reactions. These are the steps for balancing redox reactions in acidic solution. We're going to go through these steps as we balance a redox reaction. This is the figure from your book, which is just slightly different than my list, but we will look at both of them. And here we have a redox reaction occurring in acidic solution. We're going to use this reaction as an example of how to balance redox. Okay, so this is a little tutorial on how to balance redox reactions. We'll start with acidic solution. So these are similar steps that the book has. Separate the reaction into two half reactions. And then you balance elements other than hydrogen and oxygen using coefficients. Balance oxygen by adding water. Balance hydrogen by adding H+. At this point, the atoms should be balanced. Then you're going to balance charges by adding electrons. I'm leaving space here because we're going to change this for basic solution in a minute. I'm going to add in one step. Make the electrons in each half reaction the same so that they'll cancel by multiplying them by an integer, the whole reaction. And then at the end, you're going to add the half reactions back together. And then simplify anything that's the same on the left and the right. So we're going to use this example in acidic solution. So we're going to go back. We're going to do step 1, separate the reaction into two half reactions. That's here. So the chromium and the chromium are in one half reaction. The nitrogen is the element in the other half reaction. Step 2, balance elements other than hydrogen and oxygen using coefficients. Sometimes you don't need to do this step. In this case, we do because there's two chromiums on the left and there's only one chromium on the right. That means we need a coefficient of 2. That's shown here. The next step is to balance oxygen here, step 3, by adding water molecules to the sides that need them. So if we go back to our half reactions, in this case we have 7 oxygens on the left, none on the right, which means we need 7 water molecules because each water has 1 oxygen. In the right-hand half reaction, NO2 minus to NO3 minus, we have 2 oxygens on the left and 3 on the right, which means we need to add 1 water molecule to the left-hand side. Next, we're going to move on to step 4, balance hydrogen by adding H+. So here we have no hydrogens on the left, 14 hydrogens on the right, which means we need 14 plus H pluses added to the left-hand side. In our other half reaction, we have 2 hydrogens on the left and none on the right, which means we need 2 hydrogen ions on the right-hand side. Next, we're going to check the charges. I'm going to balance the charges by adding electrons. So on the left, our left half reaction, the left-hand side of that reaction, we have 14 H pluses and we have 1 negative 2 dichromate ion, which means the charge on the left-hand side is plus 12. The charge on the right-hand side is plus 6 because we have 2 chromium plus 3 cations. That means that we need 6 electrons and we need them to be on the left-hand side because electrons are negative. That's going to bring this plus 12 down to plus 6, which is our goal here. On the right-hand half reaction, we have NO2, which is negative 1, and we have 1 NO3, which is negative 1, and 2 H pluses, which are positive 2. So the overall net charge on the left is negative 1, the overall net charge on the right is plus 1. That means we need 2 electrons, and they need to be added to the right-hand side to make them both plus 1, negative 1. Just remember there's also a 0, and it goes through 0 charge, right? So we have 6 electrons on the left and 2 electrons on the right. So step 6 is we need to make both of them a 6 so that they cancel out when we add them together. which means we're going to multiply the right-hand half reaction. The whole reaction gets multiplied by 3. So you end up with 3 nitrites, 3 waters, 3 nitrates, 6 H pluses, and 6 electrons. Now our last step is just going to be to add those two half reactions together. And we're going to cancel out anything that's the same on the left as it is on the right. That's what we call simplify, right? So add the half reactions together and simplify. So if we add these together, 6 electrons should cancel out. That was the whole point of step 5. Or maybe that, yeah, step. And then we have 14 H pluses and 6 H pluses on the right, which means that this 14 becomes an 8 and those 6 H pluses go away. We have 3 waters on the left and we have 7 waters on the right, which means all 3 of these get canceled out, and that leaves you with 4 on the right hand side. So we're looking for the net simplified equation, which is 3 nitrites plus H plus, 1 dichromate, 2 chromium 3 ions, 4 waters, and 3 nitrates. We've seen how to balance redox reactions in acidic solution. We're going to modify that and balance redox reactions in basic solution. It just has one additional step between steps 4 and 5. You can actually do this step anywhere. You can do it as long as you do it before you, actually you can do it anywhere as long as you've already done steps 1 through 4. You can do this at the very end. You can do it after step 5. You can do it after step 6. So you can really do it anywhere. I think your book, when it goes over it, it just does it at the very end, which works as well. Here we have the following reaction occurring in basic solution. This is the one we're going to use as our example. Next, we're going to do this reaction. It's going to be in basic solution. So we're going to modify our steps here. We're going to add in a step 4b because we're in basic solution now. So a basic solution is going to be everything in black with the addition of step 4b, which is in green, which you only do if you're in basic solution. So you need to neutralize. The idea here is we're using things that would be around in this solution, and a basic solution is not going to have hydrogen ions. It's not going to have H plus ions. It's going to have OH minus ions. So that means you basically neutralize. Any place that you've added H plus, you eliminate that by neutralizing it with the same number of OH minuses, and those become water molecules. And then the other side, because you've already balanced all the atoms by the end of this step 4, you also, whatever you do on one side, you have to do on the other side. So however many hydroxide ions you add on one side, you have to add that same number on the other side. So let's see what that looks like with the reaction that we have here. So now we're in basic solution. And so we're going to, one other unusual thing about this reaction is that we have a single reactant molecule. And so when you have a single reactant molecule like this, and they both contain chlorine, so what's happening here is the chlorine is being oxidized and it's being reduced, right? So if you went through and you figured out oxidation numbers here, you have ClO2 on the left, which means if oxygen gets to be -2, this chlorine on the left-hand side must be +4. On the right-hand side, oxygen is still -2, but now we have an overall -1 charge here. So instead of being +4, he's +3. So in that case, chlorine has gone from +4 to +3, which is an oxidation. +4 to +3, which is a reduction, sorry. And then on this molecule is chlorate, right? So you have 3 oxygens, which all together add up to -6. The overall charge must be -1, and so this must be +5. So in this case, chlorine's gone from +4 to +5, which is oxidation. So this left-hand reaction, the half reaction I'm writing here is the reduction, and the right-hand reaction I'm writing the oxidation. Because the chlorine atom in the reactant is both being oxidized and reduced to form 2 different products. So in this case, you just write it twice. So step 1, we separate the half reactions. Step 2, we add water molecules to balance the oxygen. So that's what we've done here. They're equal number of oxygens on the left reaction, but the right-hand reaction, there's 3 oxygens on the right and there's only 2 on the left, so we need a water molecule on the left. Step 3 is to balance hydrogen by adding hydrogen ion. Since we just added a water on the left, that means we need 2 hydrogen ions on the right-hand side. Now, this is our step where we're supposed to be neutralizing these, right? So wherever we've added H+, we need to also add a OH-. I think this is the point, yeah, where I realized that I had the numbering wrong. We didn't need to do step 2, the balance non-hydrogen, non-oxygen elements. So I accidentally skipped that step. So now here, whatever we've done on the right with the hydroxide, we have to also add that on the left. Where they are combined, 2 H pluses and 2 OH minuses, that becomes 2 waters, right? So now step 5, the overall charge on the left is 0, the overall charge on the right is -1, which means we need 1 electron on the left-hand side. Over here, the overall charge is -2, and on the right-hand side, the overall charge is -1, so we need 1 electron on the right-hand side. Now we don't need to do step 6 because we already have the same number of electrons in both half reactions, and so all we need to do is add them together. So we have 1 electron on the left, 1 electron on the right. So all we need to do is step 7, where I'm going to draw this under here. I'm just rewriting the same reaction, and I'm going to add them together to get the overall reaction, which is step 7. So here, water, 1 water on the left, 2 on the right, means that 2 goes away, and then the electrons cancel. And that looks to be it. So we have 2 hydroxides, 2 ClO2s, 1 chlorite, 1 chlorate, and water. You can verify your answer by double checking that all the atoms are balanced. In this case, we have 6 oxygens on the left, 1, 2, and then there's 2 of these molecules, so that's 4. So 2 plus 4 is 6 oxygens on the left. On the right, we have 2 here, plus 3 here, plus 1 here makes 6. So that's why I put a check there, because there's also 6 on the right. 2 hydrogens on the left, and 2 hydrogens on the right. 2 chlorines on the left, 2 chlorines on the right. And then a -2 charge on the left and a -2 charge on the right. So verify that all the atoms are balanced and verify that the charges are balanced. Finally, near the end of the chapter, there is a discussion of applications of redox reactions. So one application of redox reactions are redox titrations. So these images show a redox titration of oxalic acid, which is in the flask, that's the analyte, being titrated with potassium permanganate, which is the titrant in the burette. Now you can barely see the bottom of the burette, but the color you see, that kind of dark purple color, is actually potassium permanganate. And so the titrant in this case has a color associated with it. When it reacts with oxalic acid, then as long as there's some oxalic acid still left in the flask for it to react with, then the potassium permanganate will go away and it will turn into a colorless product. So as long as the flask remains colorless, then you are not yet at the end point. Now you can see once the color is more difficult to swirl away, just like in a standard neutralization reaction titration, and you can see some remaining potassium permanganate that's trying to be swirled away in the middle, and then of course the purple color will persist on the far right once all of the analyte has been reacted away. And so it's very similar to the colored endpoint in a neutralization reaction titration. And this is a good example of, number one, titrations do not have to be acid-base titrations. They can be redox reaction titrations. Number two, sometimes in this case, the color change occurs at the endpoint, and that's always true, but sometimes the color, like here and like in the acid-base titrations, it goes from colorless to colored, but sometimes the color will just change from one color to another, or it might turn colorless at the endpoint. It might be colored. You might have colored products that once they are gone become colorless. And so there are a lot of ways to do a titration, and that's kind of the point of this problem. So here we have a problem. Potassium permanganate is used to titrate oxalic acid. If 33.45 milliliters of potassium permanganate is required to titrate 9.50 grams of oxalic acid, what is the concentration of KMnO4? So there are a lot of, this is just a flow chart that shows how to determine the answer for a titration. So of course, once you know moles of analyte, you can convert that to moles of titrant, and then that will give you the molarity in the end. And sometimes you might use this to determine the mass present of analyte, or you might use it to determine the concentration of analyte, or there are a lot of reasons why you might do this. Actually, when we standardize titrants, we use what's unknown is the concentration in the burette, and so sometimes the unknown isn't necessarily the analyte, but or isn't necessarily in the flask, I guess.